Welcome again to Let's Talk Advanced Chemistry, Chemistry 2 with Pastor Dan. We're getting started in kinetics today. Kinetics are how reactions take place, and definition of kinetics is the area of chemistry dealing with the speed or rate of chemical reactions. So how quick reactions take place. Now, factors that control rates of reactions. The first one is the physical condition or the phase. So if it's a solid, a liquid, a gas, those affect how rapidly the reaction takes place. The concentration, and I always like to show this demonstration. I do this in lab, but I don't have that.
You are about to witness one of my favorite chemical reactions, the iodine clock reaction. Various compounds can be used as reactants, and an example would be with hydrogen peroxide, potassium iodide, sodium thiosulfate.
Like that, and that's an example of concentration.
All right, so that was an iodine clock reaction. We have iodate plus bisulfite, and the reaction, because the concentration of bisulfite causes that blue-black color to be formed there. And based on how much sulfite is inside of there, how quickly the reaction takes place. And that's why you get that change on different colors. That's why it's called the iodine clock reaction.
The next one is temperature. So if it's warmer, usually the reactants for solids and liquids move faster, reaction takes place. For gases, it's the opposite. All right. And then for presence of a catalyst, we defined a catalyst before, substance that increases the rate of reaction without being consumed. All righty. Now, we're going to look at two types of reaction rates. We're going to talk about the average, which we're going to actually do, and then there's another value which you would need sophisticated mechanisms to calculate. And so the first one, the average, is the change of a concentration over a specific length of time. So we take the concentration at one point and another point, take the time difference, and identify the average. And instantaneous, that would be using an actual measurements of concentration change. We would find the specific in the moment what it would be. So let's do the average reaction. So take a moment, copy all of these down. This is the rate of disappearance of C4H9Cl over a total of 800 seconds. So let's take a first time span. Let's say we're going to go from 0 to 50. Now, we go 0.100, the final 0.0905 molar minus 0.1000 molar. We get a difference of negative 0.00905 molar. Now, we're going to get rid of that negative because all the negative means that it's disappearing. So we're finding the rate of disappearance of this substance over the time. So from 50.0 to 0.0, the difference is 50.0. Now we do our sig figs. 0.00905 molar has 3 sig figs, and 50.0 seconds has 3 sig figs, so 3 sig figs and 3 sig figs. Take 0.00905 molar, divide by 50.0 molar, and we get 0.000190 molar per second, and that, or 1.90 times 10 to the negative fourth molar per second. That would be the average rate of disappearance of that compound. Now, I want you to try this sequence on your own from 100.0 to 400.0 seconds. Find the rate of disappearance of that. So pause the video, work through that. Remember, if you have any questions, ltswpd@gmail.com. Remember, like, subscribe, share, let people know about this, comment. All right, answer here, just going to show you the answer. Answer is 0.000124 molar per second, or 1.24 times 10 to the minus fourth molar per second. All right, now, the only other thing that we're going to look at today is how stoichiometry, remember that concept of balancing reactions, would apply here. So for a reaction where we have the reactants with their exponents, their coefficients, and the products with their coefficients, what we're going to do is we're going to take the inverse, so of the rate of change of the first reactant over time. So that's the rate of the reaction of A And the 1 over B, so the inverse of that coefficient of B to the rate of change of B, is equal to 1 over C, the rate of change of C, and of D. Now you notice these are negative. Again, all those that means is that they're disappearing. They really don't matter mathematically. That's how we got it inside of there. Alrighty, so let's see how this works. Here's our first problem. Determine rate of disappearance of ozone and reaction of ozone to oxygen if the rate of appearance of oxygen is 6.0 times 10 to the minus fifth molar per second. So I'm giving you the rate of appearance of oxygen. So let's look at our reaction. We're going ozone to oxygen, O3 to O2, and balance it up. We're going to put a 2 in from the ozone, 3 in front of the oxygen. So if you look at just our two substances, the rate of disappearance of ozone is 1/2. That rate is going to be equal to, now we know oxygen. And what was that? Let's get rid of the negative. Again, all that means it's disappearing. So we know oxygen. We're looking for ozone. So we're going to take that 2 here, multiply it across. So 2/3 the rate of appearance of oxygen is going to be equal to the rate of disappearance of ozone. So let's put our value in. We know that oxygen's appearance is 6.0 times 10 to the minus fifth molar. So multiply by 2, divide by 3, and we get 4.0 times 10 to the minus fifth molar per second is a rate of disappearance of ozone for this problem. All right, I'm gonna do one more. I want you to take a second and check this out, try this on your own, and then we'll work through it. So for the second one, determine the rate of appearance of carbon monoxide in the reaction of carbon with oxygen. The rate of disappearance of oxygen is 3.45 times 10 to the minus fifth molar. Okay, now, just in case you don't know, there's a reaction. You gotta balance it up. Pause the video, work through it, see what happens. Okay? Here we go. Balance it up. There we are. And we're only looking at carbon monoxide and oxygen. Actually, we can't do carbon because carbon's a solid. So we're looking at the rate of disappearance of oxygen is equal to 1/2, because again, this is a coefficient of 2. So we make it an inverse, 1/2 the rate of appearance of carbon monoxide. Now we're looking for the rate of appearance of carbon monoxide, so we're solving for CO. So the rate of appearance of CO over time is equal to 2, because we're bringing it to the opposite side, 2 times the rate of disappearance of oxygen. Now from the problem, we see the rate of disappearance of oxygen is 3.45 times 10 to the fifth. So multiply by 2, we can answer 7.50 times 10 to the minus fifth molar, and that's my answer. All right, that's it for today. Hopefully not too bad. Take care. God bless. Bye.